Alright, so continuing with our quest to understand epsilon delta proofs a little bit more, I'm going to give you two slightly non-trivial examples. First is going to be my claim that this quadratic function has limit 10. Alright, so what we're after here is through some manner of inequality trickery, we want to show 2x squared minus x minus 5, right, minus 10. We want to make that less than epsilon. And what do we have to work with given, what are we given? We're given 0 less than epsilon value of x minus 3 less than delta because my limit point's 3, right? That's what we have to work with. Alright, so this is our given, that's our goal. Let's rewrite the thing that's our goal a little bit more and try to understand it. 2x squared minus x minus, well, 15. Alright. So that's the epsilon value. Well, here's a trick, folks. Whenever you have the limit as x goes to 3, if you did this right, what's going to happen is an x minus 3 is going to factor out. Alright, so if we were taking the limit as x goes to 2, if that was a 2 instead, it'd be like an x minus 2 we could factor out. If the limit was, if our x was going to minus 17, you'd be able to factor out an x plus 17. It will happen for these polynomial examples, alright? Unless you made a mistake. So x minus 3 is going to factor out, right? If you believe me. Well, I mean, it's factoring. We'll find out soon. So I wrote x minus 3. I need a 2x squared here, so I'm stuck. I'm stuck with it. I have no choice. I have to write 2x, right? In order to get the 2x squared back. And then, oh, I'm stuck with this too. 15. The only way I can get 15 from minus 3, minus 15 from minus 3 is to add 5. Okay, we should check ourselves. So 2x squared minus 6x plus 5x is minus x and minus 15. Indeed, it does factor. Okay, so that's going to be the epsilon value of x minus 3 times the epsilon value of 2x plus 5. Now, of course, this we can make smaller than delta, right? But this right here, well, that's a little bit different, right? If you think about it, if x is close to 3, what's going to happen to this? Well, let me just show you. If we have the epsilon value of x minus 3 is less than 1, suppose just for the sake of discussion that we're within 1 unit of the limit point, all right? That's just a choice. But if that's the case, that means that minus 1 is less than x minus 3 is less than 1. I want to find out something about 2x plus 5, so I just multiply this by 2. Minus 2 less than 2x minus 6 less than 2. I want to get plus 5. So if I add 11 to this, that gives me 9 less than 2x plus 5. I added 11, 13. Oh, so apparently if I make my delta smaller than 1, I can be confident that 2x plus 5 is less than 13. So apparently I can, oh, I have to deal with the epsilon value of 2x plus 5, right? So, of course, 9 is greater than minus 13, right? So there you go. Epsilon value of 2x plus 5 is less than 13. Provided I have what? I do need that delta is less than or equal to 1. So if I have delta less than or equal to 1, then I can make this less than 13. So I also want delta to be what? I want delta to be less than epsilon over 13, right? Okay, so now I have done enough that I can put the proof together. I'll show you how now. Alright, so here we go. Let epsilon be greater than 0, and choose delta equal to the minimum of 1, because we want this stuff in red, and epsilon over 13, because we know once we get past the stuff in red, then this other thing will take over. And I can have my cake and eat it too by making delta the minimum of these two things. Right? If I have this, right, then delta is less than or equal to 1, and delta is less than or equal to epsilon over 13. Those things are both true if delta is the minimum of these two things. And the minimum of these two things is positive because epsilon's positive. All right, so we're good to go. Let x be a real number, and suppose 0 is less than absolute value of x minus 3 is less than delta. All right. Note, absolute value of x minus 3 then is less than delta, which is less than or equal to 1. Therefore, the absolute value of x minus 3 is less than 1, which gives me that minus 1 is less than x minus 3 is less than 1, which implies that minus 2 is less than 2x minus 6 is less than 2, and hence 9 is less than 2x plus 5 is less than 13, and so we deduce the absolute value of 2x plus 5 is less than 13. Okay. Consider then the absolute value of 2x squared minus x minus 15 is equal to the absolute value of x minus 3. I'm sorry, I bad form. Oh, stink. 1 second here. That's not what I wanted to write. The absolute value of 2x squared minus x minus 5 minus 10. All right, because I'm trying to communicate to the reader here is that this, and you might write this separately. This is a f of x, and this is L, right? So we're looking at the absolute value of f of x minus L. Anyway, this is equal to the absolute value of 2x squared minus x minus 15. All right? And then, of course, I'm just following the algebra we already just did, but I have to do it again. Otherwise, the Pharisees of analysis will come and take me before the high court. Let's see here, or something like that. Where's it the Sadducees? I don't know. You pick them. So, let's see here. So that is the absolute value of, as we went through a second ago, x minus 3. Still can factor, right? 2x plus 5. But by properties of absolute value, that is equal to the absolute value of x minus 3 times the absolute value of 2x plus 5. And what I usually do in a proof of this length is I'll label things like, I'll call this result 1, right? And so this is less than delta, and times 13 by 1. I mean, that's something like that is what I would usually do. And then that is, of course, less than or equal to epsilon over 13 times 13, which of course is equal to epsilon, right? Thus, 0 less than absolute value of x minus 3 less than delta implies that the absolute value of f of x minus L is less than epsilon for f of x equal to 2x squared minus x minus 5 and L equals to 10. Thus the claim follows. All right. Now, so that's how to do the epsilon delta proof that this quadratic goes to 10. All right, one more of these, and then I think we'll have it out of our system. Now, you of course might ask me, why did you do delta less than or equal to 1? Where'd that come from? Well, the answer is very simple. Someone else showed me that. Example 5. I mean, not that specific one, but that generic trick. So, left to my own devices, I would try to come up with some sort of awful formula for delta. My next claim. But once you understand what the idea of that 1 is, it's really not that surprising, the idea. Basically, the point is you're left with some expression, you need to bound it. And since we don't know about calculus yet, in order to bound things, we pretty much have to work with inequalities. And so, let's see here. Limit is x goes to 2 of 1 over x plus 1. That should be equal to what? Well, we know, 1/3, right? So there I'm using limit laws. Of course, once we know limit laws, then we don't need to do this epsilon delta stuff, but to prove limit laws, you need epsilon deltas. So this is the nuts and bolts below the machine you've been using. Of course, truth be told, you probably haven't calculated a limit in months, and so the machine you're using is even above the level of limits, because limits go to prove differential calculus, and ultimately differential calculus leads to integral calculus, unless you read certain books like Apostle, which do integral calculus first. Anyway, this is some substructure. Certainly, if you take a course in real analysis, there's a pretty good chance you'll look at some of this stuff there, albeit in probably what seems like a more confusing fashion, depending on how you look at it. Anyway, this stuff really isn't that complicated, it's just unfamiliar. X goes to 2 of 1 over x plus 1 is 1/3. Alright, so what I'm after here, guys, is that I wanna make this inequality, right? I wanna make this thing smaller than epsilon, right? So the thing to do with that is to make a common denominator. So that's 3 minus x plus 1, parentheses are your friends. Downstairs I have 3 times x plus 1, right? So, of course, that is equal to 2 minus x over 3x plus 3. And then using properties of inequality, of absolute value, we can rewrite that as x minus 2 over the absolute value of 3x plus 3. Alright, so that's x minus 2 is good. We got control over that because we're looking at the limit as 2. So I can make that less than, delta over the absolute value of 3x plus 3. So I just got to get my paws on this expression, and I need to I need to bound the reciprocal of 1 over 3x plus 3. Okay, so I like to think of these things graphically sometimes, so let me do that. So, especially something like this. So y equals 1 over x plus 1, right, is what? This is the reciprocal function shifted 1 unit to the left. It's got a vertical asymptote over here, like -1, right? Not that that really matters much to us. And the graph is roughly speaking something like that. Now, we're concerned with the point x equals to 2, right? That's the limit point, 2. And so, on the basis of our success with the previous problem, we might want to think about going plus or minus 1 from there, right? So if we go from 1 to 3, like that, right? And then we look at this thing, right? We don't have to, actually it doesn't matter if we do consider it, but we don't have to. These values, it's pretty clear that that's 1 over x plus 1, right? I guess, fine. You're like, what's that 1 over x plus 1 you have to deal with? It's that. Fine. This is 3 times the absolute value of x plus 1, right? So, it looks to me like we can pretty clearly see what's going to happen. I can see from here 1/2 is going to be less than greater than 1 over x plus 1. It's going to be greater than 1/4, because when you plug in 1 into that, you get 1/2, and this is a 1/4, that point. So like that bounds that. Alright, so I've done enough. I think we're going to be able to make delta. So that this is, I'm running out of space here. This is going to be less than delta over 12. So I want to make delta the minimum, because I want this to be less than or equal to epsilon, right? So I want to make delta to be the minimum of 1 and like 12 epsilon, right? If I haven't made a silly mistake. Huh. It's not what I got when I did this on scratch work. Huh. What did I do? Am I right here or there, I wonder? Huh. I've got 6 epsilon in my scratch work. 1 plus 1, 1/2, 1, 1/3, 1/4. Maybe I just used, I don't know. Well, what? Sorry guys, I'm a little bit, I'm not sure where I made I'm not sure if I made a mistake in the scratch work I haven't showed you, or here. Let me look at this for just a second. So 1 over x plus 1 oh, sorry, age-old problem. This means that 1/4 is less than 1 over x plus 1, right? Is less than 1/2, right? And so that, of course, is greater than minus 1/2. And so the thing I get is that the absolute value of 1 over x plus 1, which, by the way, is equal to 1 over the absolute value of x plus 1, is less than 1/2. It's not the fourth that comes into play. So that this is less than delta over 3 times 2, which is 6. So yeah, not 12 epsilon. I want that to be 6 epsilon. That's why this is called scratch work. As you can see, it's scratchy. All right, so let's finish this thing. All right. So let epsilon be greater than 0, and choose delta equal to the minimum of 1 and 6 epsilon. Observe if the absolute value of x minus 2, right, is less than 1, then we have minus 1 less than x minus 2 less than 1, and then hence minus 3 is less than 3x, minus 6 is less than, I'm multiplying this by 3, less than 3. I want 3x plus 3 eventually, right? So if I add 9 to this, thus, if I add 9, I get 6 less than 3x plus 3 less than 12, right? Oh man, is that 12 again? Huh. Oh, I'm sorry. I'll get with it eventually here. Sorry, guys. All right. So that implies that what? 1/12, right, is less than 1 over 3x plus 3 is less than what? 1/6, right? And we also have that the absolute value of 3x plus 3 is equal to 3x plus 3, because this shows that that's positive quantity, right? Whence, I don't get to use whence too much. Whence 1 over the absolute value of 3x plus 3 is less than 1/6. All right. So suppose 0 is less than the absolute value of x minus 2 is less than delta, right? Thus, consider the absolute value of 1 over x plus 1 minus 1/3 is equal to, all right, I'm going to, come on. Well, that's equal to the absolute value of 3 minus x plus 1 over 3 times x plus 1, which is equal to the absolute value of x minus 2 over the absolute value of 3x plus 3, which by the way is less than delta, right, over 6, which by the way is less than or equal to 6 epsilon over 6, which is of course epsilon. Thus, the limit as x goes to 2 of 1 over x plus 1 is equal to 1/3. Now, some of you, of course, just got done, and there's the proof, taking a calculus 1 where you probably didn't say word 1 about this. And it doesn't necessarily mean that you're really much of a disadvantage in calculus 2. This sort of thing tends to be very interesting to math majors and to certain very inquisitive science majors. There have been a student or two over the years who have become math majors because we covered this topic in Calc 1. Maybe my best student ever, partly for that reason. And if you really care about foundations and you want to know why limits work the way they do as opposed to just, claiming that's how they work, well, this is how to make them work as we claim they do precisely. And so it's important. I mean, this method I think goes back to Weierstrass. I think he's the one that was the champion of the epsilons and deltas and so forth. The kind of rigor that is common to see in modern research mathematics, I don't think is quite like this so much anymore. But it's still important, and certainly if you're a math major, it's something you do need to master. It is expected that you master this at some point. But really, operationally, what's going on here is you need to learn how to bound things and how to have a clear understanding of what you're allowed to assume versus what you're trying to prove. And not to confuse those two things. That's the chief thing people get wrong about this, is that they assume that absolute value of f of x minus L is less than epsilon, and then they try to work back. I don't know what they're doing, but that seems to be a very, very popular sort of wrong halfway point in these kinds of proofs. But anyway, I'm not going to test this on the quiz. I'm just showing you this in case you didn't see it before, for your edification. And you can ignore it if you like. It's up to you. Thanks, guys.